Okay, today we'll take a look at these important theorems that he talks about, and we'll kind of see a few other uses of them, and later on we'll be using them as well to be able to do some of the procedures that we're told we can do. It's mainly because of theorems like this that allows us to do that. And the first one that we're going to look at is the intermediate value theorem. Now, I'm not going to go through all the details of the parts of it, but we'll use it. And yeah, this one is fairly straightforward. One main thing we use, and we've actually, kind of taken it for granted on using Newton's method, the worksheet here. We'll pick out one of those functions and show that there's at least a solution to these equations. Let's see. Let's take a look at f of x equals x to the fifth plus x minus 3, which is the function on problem 4 with our using Newton's method worksheet. Now, this is precisely I guess we would say the first step is to show that there's actually a zero for this function, or showing that, there is at least one solution to this equation. Now, we've already approximated that using Newton's method, but we didn't first say, well, yes, there is at least a solution. So we'll kind of go before what you've done with Newton's method. Now, with this, we pretty much just need to start guessing some of the function values that we have. F of 0 would be what?
-3.
Okay. F of 1 would be what? Okay, -1. Now, the intermediate value theorem would not be able to tell us there's a solution in between 0 and 1, because why? Both function values are negative. Now, let's move on to f of 2, and this will make a little more sense as we see how we can apply. F of 2 would be what?
31.
Okay, yes, 31. And the key here is positive 31. Now, one thing in the details of this theorem, the function needs to be continuous, which any polynomial being x to the 1, x squared, x cubed, x to the 4th, any whole number exponents, well, that's added or subtracted, those are polynomials. And those are the nice functions to work with. They have a lot of nice properties. Continuity is one of those properties. It's continuous for all real numbers. So it is a continuous function, and this shows us that there is a 0 in between x equals 1 and x equals 2, because one of the function values is negative and the other one is positive. Now, let's just take a quick look at the graph here of these 3 points, 0, -3, 1, -1, and then 2, and well, way up here somewhere at 31. Our units will be a little off on this case, but now, since this is a continuous function, we need to be able to draw a continuous graph to connect the dots. And without getting any more detailed, what we'll find is something like this. Okay. So, in between 0 and 1, we're not guaranteed that there is a function value that equals 0. Now, technically, there still could be, based on just these two function values. A situation might occur with 0, -3, and 1, -1. We may have a function that goes up and back down and up and down and hits 1, -1, and then goes back up. So all of these points would be considered where the function could equal 0. So just because this one's negative and this one's negative doesn't guarantee that there is not a 0 between. It just doesn't say, it guarantees that there may not be one. There still could be one, but there may not be one. But moving over between 1 and 2, x equals 1 and x equals 2, we are guaranteed that there is at least one. Because one of the y values is negative, one of the y values is positive. So because of the continuity of the function, there's a function value in between -1 and 31 for each of the x values. So we could even say, where is the function value equal to 1? Well, somewhere between 1 and 2, there's going to be a function value equal to 1, based on the intermediate value theorem. Okay. There's even an x value where the function is equal to 30, or 29, or 15.8754931. I'm not going to find that one, but we could say there is one, at least one. There may be even more than that. But that's the intermediate value theorem, and this is something you may actually have seen in an algebra course. Okay. Probably not, but you may have seen that. But it's something we can use in algebra. It's just calculating function values. And so somewhere between 1 and 2, we're guaranteed that there's at least one solution to this equation. And graphically, we can see, yeah, somewhere in there, it's going to cross the x-axis. Okay. So that's kind of a real big theorem as far as solving equations, or at least, there's two main statements. We'll get to the second one here after our next theorem, but this theorem says there exists a solution between 1 and 2. Don't know where it is exactly, but at least somewhere between x equals 1 and x equals 2, there is an x value that gives us the function value of 0. Okay. There may even be more, but there exists means at least one. Okay? So that's the first of the big ones. Now, Rolle's theorem kind of looks at things a little differently. Again, for this to work, we have to have a continuous function, and it must be differentiable. Now, differentiable, we've talked a little bit about, not a whole lot, but basically there's no cusps, there's no sharp corners in the curve. It's got to be a smooth curve. Okay. A non-differentiable function would be something like this. This function is not differentiable at this point. Okay. But it is smooth. The derivative exists at all other points, just not that one. Now, Rolle's theorem is getting a lot more specific where it has to be continuous and differentiable. So this particular situation would not work for Rolle's theorem. Okay? But if we have two different x values that give us the same y value, okay, for instance, let's say we have points a f of a and b f of b. Those are the same y values. Then there must be a value in between a and b where the derivative of that x equals 0. Well, if it's continuous and differentiable, then from A to B, we've got to be able to draw a smooth curve. And, well, it's kind of what comes up must go down type of thing. And where it is smooth, at the high point, we're going to end up with the derivative being 0. Graphically, we would say that's the slope of the tangent line. Slope of the tangent line equals 0 at that point. Now, it doesn't say what that value is. It just says there exists an x value somewhere in between a and b. So we're at least narrowing in a little bit. It's got to be between a and b, but it doesn't say what particular number between a and b. It just exists. Okay? So that's Rolle's theorem. Now, with Rolle's theorem, we're going to go back to our equation we looked at with the intermediate value theorem and give it a little more strength. Say there is a solution, but this is the only solution. Okay? So a uniqueness rather than an existence. Okay, so as I said, this shows through the intermediate value theorem there exists a solution, and now we're going to take this function and show that there is only one, not just at least one, but only one. And this gets a lot more heavy into the theory, the theorem, and shows a technique of proving things mathematically. This will be some of the ways that these theorems you run into are proven. Now, at this level, we're not going to do a lot, if any, proofs, but those of you that are going to change your major to math, I know you want to after this class, but you will, well, maybe change your major from math, but the upper level, your junior and senior level math classes, you'll get into proving things. So this is one of the techniques that is used quite often. It's very useful. And this is where we make an assumption and then actually prove that that assumption is wrong based on what we're given. Okay? Okay. So, if we want to show there is only one solution to this equation, then let's assume there are two solutions. We'll call those x sub 1 and x sub 2. And what we're saying is f of x sub 1 would equal 0 and f of x sub 2 would equal 0. Okay? Both of those x values, function value needs to equal 0 to be a solution to this equation. Okay. So, from Rolle's theorem, this is like saying f of a and f of b. Okay? F of a equals f of b doesn't necessarily have to be 0. It just, in this case, it is equal to 0. So from Rolle's theorem, since f of x sub 1 and f of x sub 2 equal the same value, we can say there exists an x value, and we'll just call it C, like we've been calling it, in between x sub 1 and x sub 2, such that the derivative equals 0. F primed of C equals 0. Okay? Well, let's see what the derivative is for our function. X to the 5th plus x minus 3 . Now, Rolle's theorem says there must be a value where this is equal to 0. Well, as we try to solve for x, subtract 1 from both sides, divide by 5, there is no x value, at least within the real numbers. We'd have to get into the complex numbers, which get even more interesting. But we'd have to say no real solution to this. Well, that goes against what Rolle's theorem tells us. Everything that we have looked at, everything fits with Rolle's theorem according to our assumption. But Rolle's theorem would be deemed untrue, okay, which, if everything fits into our, all of the conditions are met in Rolle's theorem, then it should come out to be where there is a solution. The only thing that we can say is our assumption is wrong. So what did we assume here? What did we state as our assumption?
It would be two solutions.
Two solutions for the equation. That is false. So what does that leave us with? There is only one solution to this equation. Okay. So, with the intermediate value theorem, that says at least one solution. Rolle's theorem says only one solution. So we tie those two together and we can say this equation, throw some fancy terminology at you, has a unique solution. What do you think unique means? One and only one. We can't just say one solution. We could say one solution is this and one other solution is this. No, one and only one. So it takes into account there's at least one, a solution exists, and there is only one. It is a unique solution. Question?
Okay, so of the two solutions,
It's just that you get a negative.
Yeah, going back up here, the assumption that we made is the only thing that could be wrong with what we've done. So we have to say, well, Rolle's theorem would work if our assumption was correct. Our assumption's not, or Rolle's theorem does not work, so that guarantees our assumption is wrong. So there cannot be two solutions. That means there has to only be one solution.
Is that
Yep.
because some equations, when you do the... Oh, yeah, yeah.
Now the mean value theorem kind of generalizes Rolle's theorem a little more. We're not looking just at f of a equals f of b and then the derivative would equal 0, but we have the conditions for Rolle's theorem except for f of a equals f of b. So essentially what this would mean, if we take, say, these 2 points, and, well, what's this formula show us? Slope of the line between those 2 points. I wish I could draw a straight line. That's supposed to be a straight line, by the way. The slope of that line is equal to the slope of a tangent line, at least one tangent line in between A and B. And as we kind of move along, maybe about that point right there, this again is an existence theorem. There's a point, an x value, in between A and B where the slope of the tangent line at C is equal to the slope of that secant line, as we call it, the line between those 2 points. Now, what I want to point out here doesn't have anything to do with the graph, but think about the derivative equaling velocity. Now, I don't know if any of you have gotten speeding tickets or not, but this is applied with speeding.
Wait, how?
If you are clocked, if you're timed, and most of the time they clock you in a 1 mile situation, but the change in distance divided by the change in time, let's say you're going 75 miles per hour, or let's say at one point you're going 85 and at another point you slow down and you might only be going 65, but you still get a ticket.
But because it
What do you get a ticket for? Well, yeah, they cannot prove that you were going 85 in this time period because you went from 85 down to 65. But because of the mean value theorem, they can prove that you were going the average of that. And that will be what you get your ticket
Wait,
for.
wait, wait. Can you explain that again?
Okay. If you're going 85 at one point and 65 at, then somewhere between you were going maybe 75. Okay. it will be based on time, really, the change in distance over change in
Yeah,
time.
that's like
They
average.
can prove that you were going 75. Even though at one point you were going 85, you slowed down
That's
enough.
like when we were doing velocity.
Yeah.
Changing.
Yeah, velocity.
Can you explain
They're
this?
calculating the average velocity from one point to another point,
Yeah, mean beach back. Oh.
which proves that the velocity was, the instantaneous velocity at some time was the same as the average velocity.
Which is found in the derivative of the position.
Right. So you may not have been going that fast the entire time period, but they can at least prove that you were going speeding over a certain time period. So that's one quick way. If a police officer pulls you over and said you were speeding, they may have caught you on with a radar gun, which that would calculate exactly instantaneous velocity, or they may have timed you over a certain distance and can prove you were going at least 75 in a 65 or whatever.
Can,
So,
I don't know if radar
yeah.
guns do that.